Hey guys, welcome back. So in the previous videos, we talked about activating, deactivating groups, as well as ortho para directors and meta directors. So we're going to talk about now how we actually can, more apply them to the actual problems, right? How we actually do the problem solving. So the thing to know is when you have multiple substituents on your benzene and you're trying to figure out, well, okay, if I have, let's say, like in this example, it says choose the structure that is most likely to be the major product of the following reaction. So we have this oxygen with that methyl, right? That's called the ether. And we have this methyl over here. So if we looked at this chart over here, they're both ortho-para directors. Here's that methyl, and here's OCH3, right? Or OR group, doesn't really matter. So they're both activating groups, right? They're both ortho-para directors, but which one do we pick to use for this reaction over here? Because if I use this guy as the ortho-para director, and let's say I pick the para spot, that's here, whereas the para spot for the methyl would be here. So they don't both give the same product, right? So the way we do it is you pick the stronger activating group. The group that is more strongly activating is going to be the group that directs the most, right? That's going to be your directing group. That's the group you want to examine. So between the ether and our methyl, ether is going to be more activating, so we're going to go with this guy, right? He's going to be the one that we look at. So we're doing this Br2 over FeBr3, so you know that adds a bromine, and we're going to put it either the ortho or the para position. Now, usually when we have something large, we put in the para position, pretty much like this OCH3 group. While we do get some ortho and some para, the predominant product would be the para product. So if I were to draw this, let's draw both possible products. So here's our O methyl and the methyl. Now in this case, we have this one ortho spot open. So that would mean the Br goes there. Can't put it where the methyl is. Para product would look like this. That will be the predominant product in this case, so making the answer B. Alright, so that's how we would do that question. Now let's move on to this one. Select the major product of the following reaction. So we have this benzene with the methyl, CF3, and again Br2 over FeBr3. CF3 is a strong deactivating group right here. Methyl is a activating group, weakly activating, but still activating. So remember, we always look at the activating groups to direct. So in this case, we want to direct with the methyl. We're looking at the methyl. So methyls direct ortho and para. Now methyls are small enough that they can direct ortho as the major product, right? But we need to be careful here. There are two spots that are ortho and one para right there. Let's put the para in a different color. All right. If we put it at that spot at the ortho, we're going to get this product. Now, that could be problematic because we have to consider sterics. All right, when you have two things on a ring, you always want to look at the sterics. This CF3 group is massive. It's a carbon with 3 fluorines. Those fluorines, think about them, they're like a helicopter. They can spin around, right, blocking off all this area. So to put the bromine there is not a good idea. The chance that it'll go there is going to be low. But there's still the other ortho position. So we have CF3. We can put the Br right there. That definitely works. That's not sterically hindered. The methyl is pretty small, and we have all this open space over here, nothing touching it. So that works. That could be one of our answers. We could also put it at the para position. Right, the para position is pretty favorable. So usually things end up going there. So in this case, that's going to go there. That is favorable as well. Now you may be wondering, well, okay, well, why did we put in the para position if that spot is also next to the CF3? Well, The problem is when we had it here in this Br, it's next to the methyl as well. Remember, the methyl still has hydrogens like this. So it's also acting like this helicopter. In this case, there's nothing over here. So that frees it up. So in this case, the para and the ortho, but ortho over here will be our major product. We don't want to have this ortho product. So we're not going to have all three. We're not going to have both orthos and the para as the major product. We're only going to have the para and one ortho. So let's look at what our options were here. So here is the one we did not want, so let's cross that out, 4. So anything with 4 we'll cross out. And we wanted this guy, and we wanted this guy over here. Now this is the meta position, so remember, we don't want that. Methyls are ortho-para directing. So choice D is going to be our answer in this case, all right? 1 and 3. Let's look at this guy. Choose the structure of the major product of the following reaction, okay? So don't get scared by this. It's a little bit complicated. So we have these 2 benzene rings, right? So look at this benzene on the left. This one is connected to this ketone, all right? If we look over here, you have this CHO. It's an aldehyde, right? It's similar enough. And that is going to be a withdrawing group, right? These are deactivating groups. So that means this benzene is deactivated and does not react as fast as a normal benzene would. So let's look at this benzene over here now. He has this alkyl group, right? I know that the aldehyde, or the ketone, sorry, is still connected to it, but the ketone is too far away to do anything. It can't withdraw electrons from it. It can't, let's say, resonate up and give the oxygen a negative and create the carbocation here and remove electrons from the benzene because it's too far. So what we do is we're going to just treat this as if it's an alkyl group right here, right? As if the carbon here is just another alkyl group. And so that's an activating group, weakly activating, but still activating. So this benzene is reacting faster than the normal benzene. It's activated. So what I'll do is I'll just draw arrows up or down, up for activating, down for deactivating. So this benzene at the right, he's going to be activated. Benzene at the left is deactivated. So first, before we even do the reaction, we need to pick which benzene we're even going to do it on. And that's going to be the one that's activated. So right there. And now, let's see if we're going to, because we're treating this as an alkyl group, it's ortho-para directing. So are we going to get para or are we going to get ortho? Well, we have this large group here. Think about it. This is one huge substituent. Imagine, since these are still single bonds, this swings around. Now you have this benzene with this carbonyl flying around like a helicopter. So the ortho positions are going to be a little bit sterically hindered. So we're going to probably go para. So let's draw that. So here's our directing group. It's on that carbon. So the para position would be right there. So we put this chlorine right there. All right. That would have been the answer to this question. Now, one thing I haven't mentioned before, and it's very important to understand. If we do Friedel-Crafts acylation, so let's say I have a benzene like this, and I do some sort of Friedel-Crafts. Doesn't matter what I'm putting on here, so I'm going to put an R group, AlCl3, and I get this. Let's think about what we just did. We just put this aldehyde, this ketone on. This means we just made this benzene, and we added a deactivating group. All right, so we just deactivated it. Once you do this, you cannot do another Friedel-Crafts acylation. It's too deactivated. All right, so watch out for that. Once you've done a Friedel-Crafts acylation and your ring is deactivated, so once your ring is deactivated is the major part, you cannot do another Friedel-Crafts acylation. If there was something else on this ring that can still make it very strongly activating, that's one thing. But in this case, because this ring is now deactivated compared to a normal benzene due to the withdrawing groups, we cannot do another Friedel-Crafts acylation, right? So pretty much whenever you have a deactivated ring, no Friedel-Crafts acylation. All right, so if I had this nitro group, we cannot do this reaction. It does not work. And you will get, if you're doing a synthesis, you could get points off of that. So no Friedel-Crafts acylation on deactivated rings. All right, hope this video helped you guys, and I will see you in the next one.